Okay. Okay, everybody all right? We seem to be losing people more and more. I hope everybody's watching the videos. Yeah. Okay. Okay, so remember what we're doing. We're on inner product spaces. And the theme is basically like anything you can do in Euclidean space, you can do in inner product space, right? Like geometrically, we're extending all these sort of geometric notions of angle and Pythagorean theorem and this sort of thing to abstract inner product spaces. Okay. Okay. So there's one more thing in this section that is a little bit, it may seem a little bit odd to include, but it's called the abstract norm. Okay. Okay. And norm meaning like the magnitude. Okay. So let me put up the definition. You have a vector space. You have a vector space, and if there exists a function that will write like the magnitude, okay, if there exists this function that goes into R with the properties that you would want a magnitude to have, right? First off, that the magnitude is always greater than or equal to 0, and is 0 if and only if the vector is 0, the 0 vector. 2, that the magnitude of a scaled vector is going to be, well, what should this be? The magnitude of some constant times your vector. What am I going to write over here? There's a little bit of a trick to it, but Ellie goes first, I think.
That you could just, it's the norm times the scalar, like outside of.
Almost. That was the trick. You need the opposite value. Yeah. So for all scalars. And then 3, you'd like the norm to satisfy this one, that the norm of a sum is less than or equal to the sum of the norms. The so-called triangle inequality. Okay. So if all three of those things are satisfied, then we call this function a norm. Okay, and we call V with the norm a norm vector space. So this is actually like independent of the idea of inner product space. So you can have a vector space and this sort of function on it, and it'd be a normed vector space, even if it's not an inner product space. Okay, so it's like a more general notion, but it is true. So remark, if V is a vector space, I'm sorry, if V is an inner product space, then letting the norm of V be defined as V against V to the 1/2 does define a norm. Okay, so what you're saying is that any inner product space is automatically a normed vector space. Okay. But the opposite isn't true. You don't, if you're a norm vector space, there's not necessarily an inner product that creates that norm. Okay, so let me make a sub remark that you actually need to check this. We actually need to check this, right? So we would need to check that that all three of these properties hold. And the only tricky one is the last one. The last one, you need actually to use Cauchy-Schwarz. Okay, so okay. Okay. There's another definition, that of distance. So given a normed vector space, we with the norm, we can define a distance. The distance between two vectors is going to be the norm of the difference between those vectors. Okay, and this will have certain properties, but anyway, yeah. The point here is simply that again, you can sort of create some sense of geometry on abstract spaces, right? So you can talk about how close one function is to another function, right, or this sort of thing. Okay, let me put up some important examples. Of norms. Okay. One, norms on Rn, actually. One is, say if you have some vector in Rn, there's something called the L1 norm, where what you do is you take just the sum of all the absolute values of the components in I equals 1 to n. Okay. Right, so if I have a vector, 1, 2, 3, then you just take the sum of all the absolute values, it would be 6. Okay. So this is called the L1 norm, or actually the little L1 norm. Two, a generalized version of that, the little LP norm, where you take the sum of the components to the pth power, and then in the end raise the whole thing to the 1 over pth power. Okay. So this one might be a bit more familiar. So like if p is 2, then that's the norm that you're used to, right? You take the sum of the squares of everything and then take the square root of everything, right? So this is just a generalization of that, right? You take it to the pth power. P is assumed to be greater than 1. This is little LP norm. And then there's something called the L infinity norm. And for that, you take the maximum of all the values. So little L infinity. Okay. Just for amusement, like if we're in R2 and I say, like, what things have size 1? So if we're using like the L2 norm, and I say, give me the guys where the L2 norm is less than or equal to 1. Well, what does that look like? That's going to be like summation, it's going to be x1 squared plus, sorry, v1 squared plus v2 squared, quantity square root is less than or equal to 1. Right? You know what that looks like, right? That's just a circle, the unit circle, and everything inside it. Right? Right. What if I said the L infinity norm is less than or equal to 1? That would be the maximum of the absolute values of the coordinates is less than or equal to 1. What does that look like? Or can anybody name some points that have L infinity equal to 1? L infinity norm equal to 1? So remember, this is the maximum of absolute value v1 and absolute value v2. So yeah.
Is it a square?
It's a square. Perfect. Yeah. This is it. This is the unit ball, right? This is the unit ball in L infinity. What about the L1 norm? Well, in that case, you're taking the sum of the absolute values of the components, and you want that to be equal to 1. What's that? This is just for fun. Yeah, Izzy.
Would that be the unit circle with nothing inside of it? No.
Right. So the coordinates, right, v1 plus v2 needs to be less than or equal to 1. Right. Can anybody name some points that satisfy that? Thank you. Origin.
Is it like a diamond?
It's a diamond, yes. Yeah, that's going to be the unit ball for L1. And interestingly, as the p's progress from 1 and head off towards infinity, actually what you get is that this thing sort of becomes fatter and fatter, and then turns into this ball, right? Turns into the disk, and then the disk starts fattening out, like sort of like this. And as p tends towards infinity, it tends to this thing, right? And then for p less than 1, you start getting some convexity. Oddly, that turns out to be useful in machine learning when they're trying to minimize some sort of error. Sorry, I don't remember exactly. All I remember is that it's useful in machine learning. Okay, so yeah, okay, let's go on to section 5.5. So 5.5, what are called orthonormal sets. Okay, one way of thinking about this section is that we're trying to get coordinate vectors in inner product spaces. Okay, so like we have the inner product space. We would like to, express things as linear combinations of other things. Okay. Okay. So motivation. Maybe this is a bit better. We want in inner product space something analogous to the standard basis of Rn. Right? In Rn, we've got the standard basis, right? E1, E2, right? E1, E2, E3, right? We'd like to have something like that in the abstract inner product space. And so, we just define it. We say if V is an inner product space and V1 to Vn are vectors in V, and they're non-zero, if the inner product of one against the other is always 0 for I not equal to j, then we call these guys an orthogonal set of vectors. Okay. It is kind of an obvious definition, right? If everybody is orthogonal, we say they're an orthogonal set. One example, if B is the continuous functions on negative pi pi, and the inner product is defined as the integral of one function against another function divided by pi, then we saw earlier that cosine x, sine x are orthogonal. Right? We saw that earlier, right? You integrate one against the other, and you get 0, or at least we said that it was true. And in fact, if we throw in 1 cosine x, sine x, cosine 2x, sine 2x, etc., and in fact, all of these guys are orthogonal. Okay, so here's an example of an infinite set of orthogonal vectors in this vector space. Yeah,
for it to be an orthogonal set, does every single vector in the set have to be orthogonal to every other vector in the set?
Yes.
Okay.
Yeah, so that's what this says. Like
Okay.
if the inner product is 0, whenever, right, for all I not equal to j.
Okay.
So whenever I is not equal to j, the inner product is 0, then we call them orthogonal. Okay, so questions?
There's a lot of music for the admins too.
Yeah, it's not normally like this. That's yeah, you have to sort of look under look under the disguise. Okay. Sorry. properties of orthogonal sets. Properties of orthogonal sets. One, if you're orthogonal, then you're linearly independent. Okay, so proof. Let's say that V1, I think Vn, is these guys, this is orthogonal in some inner product space V with an inner product. Okay. We want to show that they're linearly independent, that the VI are linearly independent. Okay, does anybody remember what linearly independent means? Okay, somebody tell me what linearly independent means. Yeah, I may have given you too much information, right? Like, that is, your brains may be full. Anybody other than Izzy, tell me what linear, yeah, Ava.
If C1, V1 plus dotted off as Cn, Vn equals 0 implies that all C1 through Cn have to be 0.
Exactly. Right. So like, in other words, we want to show, i.e. that if some linear combination is a 0 vector, then all the Ci must be 0. Okay, so let's say, let's suppose summation Ci Vi equals the 0 vector. Okay. Now we want to show that that all the coefficients must be, each of the coefficients must be 0. Okay. So what we're going to do is we're going to pick off one of the coefficients. Okay. And the way we'll do it is say, fix some j. Okay. Fix some j, and then take the inner product of Cj. I'm sorry. Take the inner product of Vj against that 0. Okay. What happens when we do this? I mean, this is 0, so we get 0, right? 0 equals this. But also what happens when we take this against this? This guy is orthogonal to everybody here except for itself, right? So what happens? What do we get? Take 10 seconds and write down what do we get here. Okay, does anybody want to say what we get here? Like if we were taking V1 against this thing, what would we get? Hello.
Well, the only one that would remain is the CJ, VJ. 'Cause
Exactly.
It's the same one.
Yeah, so this is going to be the same thing as this against CJ, VJ, right? Because everything else becomes 0, right? And so what do you get? You get CJ, you can pull out that CJ by linearity, and then you get the norm of VJ squared. Okay, but that's 0, right? We said that that's 0, right? This sum was 0. So this is 0, which means that Cj must be 0, right? Because the Vj's are all in that orthonormal set, and we said that the orthonormal sets don't have any 0 vectors in them, right? They were all non-zero vectors, right? So that tells you that Cj is equal to 0, but that was, that was just some arbitrary j, so we know that it's 0 for everybody. Right? So j was arbitrary. So, right, so C j equals 0 for all j. Okay, right. So orthogonal means linearly independent, right? So in particular, right, if these guys are orthogonal, then their basis for their span, right? You take the span of them, of course, they span it, and they're linearly independent, so they're a basis. Okay, second remark. Notice that if the norm of Vj were 1, then we could pick off Cj as then this number would be Cj, right? Then we would just get Cj here, right? So we would get Cj is going to be the inner product of Vj against these other guys, right? The point is that if our vectors are of size 1, then it's actually pretty easy to get the coefficients off, right? You just take the inner product of that vector against the linear combination, and that will give you the coefficient of that vector. Okay, and so that kind of motivates this definition, which is that if all the norms are equal 1, and the Vj are orthogonal, then we call the Vj an orthonormal set, orthonormal set of vectors. Okay, so orthogonal vectors and then orthonormal vectors. Right. Orthogonal just means perpendicular. Orthonormal means orthogonal and everybody's size 1. Everybody's been normalized, divided by their norm, so that they are norm 1. Right, so dumb comment. If V1 and Vn are orthogonal, then if you normalize everybody, let V1 over its norm up through Vn over its norm, then these guys are orthonormal. Right? So whenever you have an orthogonal set, you can get an orthonormal set out of it just by dividing it. So okay, even dumber definition. Sorry, a basis that is orthonormal. Why am I even reading this? Is called an orthonormal basis. But these things are important. We'll be dealing with them a lot. But it's the definition is dumb, but the idea is important. So, for example, you remember we had this thing, 1 cosine x, sine x, cosine 2x, blah, 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 up to say like cosine nx, sine nx. Right? This is orthogonal with respect to that inner product that we put on earlier, right? With respect to this thing. And if you calculate the norms of everybody, the norm of all these guys are norm 1, except for this one, which is norm square root of 2. So then, if you divide this guy by square root of 2 and put it, everybody else is the same, this is an orthonormal basis. Okay. So this is just an application of the dumb comment, right? That you have an orthogonal, sorry, is an orthonormal set. Sorry, I shouldn't say an orthonormal basis. Yeah. Ellen.
Why wouldn't it be a basis?
Well, I mean, it's a basis of its span. It's true.
Yeah.
Yeah. So yeah, you could say that. That's kind of a meaning.
Different kind of.
It's true. You could say that. I guess the reason I don't want to say that is because really what one would like to talk about is the space, the vector space of all continuous functions. All continuous functions. And in that case, this is not a basis of that set, because there's still a lot more. This is actually infinite dimensional. That's finite dimensional. So. Okay. Okay. Let's talk about orthonormal bases. So this is important. Useful properties of orthonormal bases. Okay. The first one is, we've kind of done this already, but if u1 to un are an orthonormal basis for V, if little v is some linear combination CI UI, I ranges from 1 to n, then C sub I is just V against UI. Right. That is, you can pick off the ith coefficient by taking the inner product against the ith vector. Right. Do I need to show that? We did that already. We basically did that. Okay. But what the point is that in other words, V can be written as summation V UI. Okay. Every V can be expressed as in this way, right? You know, it's a linear combination of the basis, And the coefficients are exactly these things. Okay. Corollary. And this is kind of a nice one. Again, say that u1, is an orthonormal basis of V. If you have two vectors, U being summation AI ui, and V being summation BI ui, then the inner product of U against V is going to be what? This one is kind of a tricky one. Okay, let's just work it out. Let's think. If we take U against V, well, that's going to be summation AI ui against V. Right? That's just, U is this, so I'm just substituting for U. Right? By linearity, I can pull out the sum and the constant. So I get AI UIV I equals 1n. Okay. So I can pull out the sum, and I can also pull out the addition, and I can also pull out the scalar multiplication. Okay. But what's UIV? UI against V is going to pick off the coefficient, BI, right? So this thing is just BI. So I get summation AI BI. Okay. So that gives me summation AI BI here. So, yeah, here's the proof. Here's the proof. Okay. Let me sort of try to show you why this is kind of cool. So here's a picture. Here's a picture. So you have this vector. Like here is our inner product space. Right. Here's our inner product space V, and in there we've got these two vectors, U and V. Okay. Now, with our orthonormal basis, right, this U corresponds to a bunch of coefficients, right, A1 through AN, right? Like this is the coordinate. This is basically the coordinate vector of U with respect to the orthonormal basis, right? V also corresponds to a vector, right? And the point is that if we take the inner product of U against V, that actually turns out to be equal to summation AI BI from I equals 1 to n. What's that, right? Summation AI BI from I equals 1 to n is the dot product of these two coordinate vectors, right? So this actually turns into the dot product of the vector A against the vector B down here, right? Right? Yeah. So it's like the orthonormal basis gives you this correspondence between the inner product space and Rn. Right? Right? Because we have the orthonormal basis, we can take this thing to here, and then the dot product actually gets preserved. The inner product here actually just turns into the dot product of the corresponding coordinate vectors. Okay. So yeah, so that's the picture. The last thing, yeah, I think that's probably the last thing. Yeah, the last thing I'll show you is a consequence of that called Parseval's formula. Which just says that if V equals summation Ci Ui, then the norm of V is going to be summation Ci squared, everything to the 1/2. Okay, but the proof of that just follows from the previous one, right? The norm of V is the inner product of V against itself to the 1/2, right? By definition, right? But the inner product of V to the 1/2 is just going to be the it's just going to be the vector C against itself, right? So it's summation Ci squared, right? That's just going to be the dot product and then raised to the 1/2, right? Which you see is just the Euclidean norm, right? So this is in Rn, right? This norm is in V, right? The norm in V, the norm of the vector in V is the same thing as the norm of the coordinate vector in Rn. Okay, so if you want, we have sort of another correspondence, right? If you have a vector here, then if we're looking at the norm here, that corresponds to the norm of A down here. That equals the norm of A down here. But that's really just a consequence of this. So it's not really anything new. It's a consequence of that last one. Okay, so it's sort of like you can take information about the original vector space and then translate it into information about vectors in Euclidean space. Okay, so we'll do more of this next time. Although I'm not going to be here on Monday, so I'm not going to be here on Monday because I'm taking my daughter to see Princeton. So, yeah, I may record a lecture over the weekend if I think we're not going to finish everything that I want to finish in this class. But I think we probably will finish.